Hello students, welcome to the series of lectures on digital speech processing. So in this video I'm going to explain about classroom discussion topic on modified short-term autocorrelation function. So in the previous video we have already seen what is the autocorrelation function and how we can apply the windowing techniques to it for a speech signal when you consider and according to the length of the window, and we are going to be taking the segments of the speech and that we are calling as the short-term autocorrelation function. Okay, now in this video let us get details about the modified short-term autocorrelation function. Okay, it is very simple topic and much discussion will not be required because we also aware what is the short-term autocorrelation function. Okay, all right. So this is the lecture learning outcome. On completion of this lecture, you'll be able to illustrate the modified short-term autocorrelation function, and you can also see the difference. Mathematically speaking, what is the major difference between the normal short-term autocorrelation function and with modified short-term autocorrelation function, and the pictorial representation also you can easily identify this. Okay, that also we can see in this video. Alright, this is the original version that we have already seen in the previous video, Rn of k, which is normal short-term autocorrelation function. So it is taking summation x of n plus m into w of m and x of n plus k, that is k samples, and which is shifted by k samples, and we'll be taking the window by k samples. Okay, so this is a normal mathematical expression that we already know. Okay, so let me recall the same thing for you to understand better. For autocorrelation function, nothing but we are going to be multiplying the same sequence with itself, taking the one sequence as an x of m, for instance, and other sequence like x of m plus k. That is, it is a shifted version of the sequence that you are considering. Okay, and how much that we are shifting, mathematically speaking, if I write summation x of m into x of m plus k, it is shifted by k times, where k nothing but the k samples you are going to be taking. Okay, so then we are going to be multiplying and then you can sum up. So that way how we are calculating the autocorrelation function. Okay, and when you apply any kind of the window techniques, the normally rectangular window we are going to be considering. So for instance, if I draw the rectangular window, should be like this, it is starting from 0 to L minus 1. This is the length, length of the rectangular window. So assume this is a rectangular window. Okay, now we are going to be taking, for the speech signal, you are applying this rectangular window, how many number of samples that you can accommodate, and that many samples you are going to be considering, and you are dividing the complete speech signal into the slices of segments of speech signal, and you are taking and you are calculating the autocorrelation function. So that we are calling as a short-term autocorrelation function. Okay, now so coming to this today's discussion more on modified version. So what is the major difference that you can observe when you see the mathematical expression? So this I am calling as a Rn cap of k with equals to summation x of n plus m into w1 cap of m into x of n plus k into w2 of m plus k. Okay, so when you take x of m should be like this, or x of n plus m we can call. So this is the x of n plus m, for instance, and again we'll be having x of n plus m plus k, which is starting from here, for instance. It will go like this. Okay, so clearly we can identify the difference. It is shifted, it is shifted by k times. So this is nothing but k samples. Okay, k samples. So first one is x of n plus m and the second one is x of n plus k. Okay, which is shifted by k samples. That way you need to understand. Okay, if you take the sinusoidal waveform like this, we can easily understand. So now when you see the modified version, we'll be having, you know, x of n plus m into w1 cap of m into x of n plus k into w2 cap of m plus k, that we need to focus. Okay, now let's get in detail about this. So Rn cap of k, that is, you know, x of m into w1 of n minus m, x of m plus k, that is shifted by, you know, w2 of n minus m minus k. So where w1 now cap, which is the standard L point window, and w2, which is the extended window of the duration L plus k sample. That way you need to understand this, because the rectangular window size is 0 to L minus 1. Okay, so total L plus k sample that can be obtained for, you know, for the extended window version. So where k is the largest lag of our interest, and we can rewrite the modified autocorrelation as, so this is a modified autocorrelation function that you are seeing here. So summation x of n plus m into w cap of m into x of n plus k into w2 of m plus k. Okay, so where now we need to define what is w1 cap of m, w2 cap of m. So here we need to understand w1 cap of m equal w1 cap of minus m. It is following the symmetry property. w2 of m equal w2. Okay, so which following the property of symmetry, please understand. Okay, so this is the symmetry property. And for rectangular window, we choose the following, you know, for w1 cap of m equal to 1 when the length of the window is varying from 0 to L minus 1, and w2 cap of m equal to 1 when the length is L minus 1 plus k. Okay, that way you need to define. Okay, so this is my rectangular window, for instance. It is starting from 0, m equal to 0, and then it just goes L minus 1 times, if this is the w1 of m. Okay, so that way you can visualize. And when I draw the representation for the rectangular window for the next sequence, which is w2 of m, please understand what is the difference. So it is starting from 0 and then L minus 1 plus k. That's all. L minus 1 plus k. So that way you need to understand. That is the way how we are going to be designing the rectangular window. Now, which gives us Rn cap of k is equals to sigma x of n plus m into x of n plus m plus k. So which is the autocorrelation function, the modified autocorrelation function that I will be having. So always use the L samples in the computation of Rn of k. For all k, we are going to be taking like this. Okay, and you should distinguish the value of k here. This is k, we are going to be taking the samples, you know, how we are going to be taking the value of the window. Okay, so that way you need to understand. And these are the examples of the modified short-term autocorrelation function. So this is the speed signal that we will be having. Okay, and when you see here, this is a rectangular window we have applied for 0 to L minus 1. See the limits 0 to L minus 1, and this is an extended version, x of n plus m into w2 cap of m. Okay, and whose limit is L minus 1 plus k, or L plus k minus 1. So where Rn cap of k is a cross correlation, which is not an autocorrelation, and this Rn cap of k is not equal to Rn of minus k, which is not following the symmetry property. So Rn cap of k will have a strong peak at k equal to p for periodic signals, and will not fall off for large k. That you need to understand. Okay, so we'll have a strong peak at k equal to p. The periodicity it is going to be calculating from that. Okay, so this way you need to understand the examples of the modified short-term autocorrelation function. This is another kind of example how we are going to be taking that. So rectangular window, and this is the dotted version, which is nothing but the dashed curve. We are going to be calculating that for the extended version. Okay, this is an extended version of a window. Okay, now ultimately we'll be seeing that how we are going to be calculating each and every short-term autocorrelation function we applying the rectangular window to it. So this is by putting all the points onto the plot, and when you take the value of L is equals to 401, and this could be the waveform that you'll be seeing. And if you use a rectangular window actually, so these are the kind of pictorial representation that can be happens. So you can clearly visible this is a short time autocorrelation function, and this is the modified short time autocorrelation function. See the difference, the peak will be high in this. Okay, so that is the difference actually we are going to be noticing. And this is an unvoiced signal. Okay, so these two are the voice signal, and this is the unvoiced signal. Please understand, here also the same thing. Okay, and we have changed the values of L, from 401, 251, 125, like that. So what you need to observe is that the peak will be smoother. Okay, so when you increase the value of L, the peak of the signal will be smoother. That way you need to understand. Okay, thank you students, thank you for watching this video.